All right. And as promised, I am back for definitely this time we will talk about exact equations. I want to start, so where I want to start though, the reason I kind of have, honestly, this section 2.3, but this is section 2.4 before this section. So I want to start with where we ended last time. So we were looking at first order linear differential equations. And where we ended is as long as we could, as long as we had a first order linear differential equation and it was in the standard form, then what we figured out is, what we figured out is kind of a nice method. So in some sense, it's, what do you call it? It's very specific. You have to have a first order linear differential equation, and it has to be in standard form. But as long as you got that, the nice thing we got was that um, we had one method that would take us through every time. All we had to do was create this integrating factor. That integrating factor ended up being the exact thing that when you multiplied it by both sides of the equation, in particular the left side of the equation, the key was the left side of the equation. The left side of the equation ended up being basically the derivative of two functions multiplied together. So it literally was the product rule of some kind of phantom function that we previously started with. And that phantom function, when you take the derivative, that the result was exactly what that left side is. And so again, the nice thing was, as long as it was that type of equation and in that form, that worked every time. So a good thought coming off of, or at least for me, a good thought coming off of that section and seeing that method is, well, like that idea of basically this left side of the equation being the exact derivative of some kind of phantom function that you started with. Wouldn't it be nice if we could pull that method, that pattern, if we could basically pull that method for a lot larger number of differential equations. So like that one applied to very specific ones, and you needed to multiply by an integrating factor, but just as an experiment of thought. So actually, I forgot this is the way I kind of want to present this. So actually, I'm just gonna make up a first order linear differential equation. And what I want to do is I want to not necessarily go through all the solving of this, but I just want to diagram out kind of what we did with the method in the last video. And then we'll kind of talk about, wouldn't it be nice if we could do this for a large, more in general for a lot larger set of equations. But basically what we saw last time is, let's say our equation, and I like the prime notation a little better sometimes. Let's say our equation was something like the following. Well, no. Let's say our equation was something like the following after, let's see. So let's say it was 2. So after we multiply by the integrating factor, let's say we ended up with 2x y prime, and let's see. 2x y prime. I had it reverse in my head. So let's do this. X squared y prime. And let's say we end up the left side of our first order linear differential equation after you multiply with the integrating factor ends up looking like something like this. 2x, right? And I don't know what's over here. Let's say it's 4x cubed, something like this. So again, what we did last time is we'd have some first order linear differential equation that started with just y prime plus, plus a bunch of other stuff. And we found the integrating factor, we multiplied through. So after we multiply through, let's say that the differential equation looks like this. So what we would do from here is realize that there was two functions that we started with. So one way to think about this is literally, there was two functions that we started with originally, that when you take the derivative of those two functions multiplied together, you get this little combination here. So really quick, just to jog your abilities of memory from the last lecture. if this is what we end up with after we multiply with the integrating factor, what are my two functions to begin with that I took the derivative of to get this left side? And I won't even pause, I'll just give you guys a second to figure that out. Mhm. Good, so you might see this pretty easily that this is, your two functions are x squared and y. This is d dx. Well, I'll write that, yes. So the two functions are x squared and y, and when you take the derivative, so what I'm gonna do here is I'm saying, when you take the derivative, you get these two pieces just because of the product. It's not anything special there. It's just that's how the product rule works. You're gonna do x squared times the derivative of y plus y times the derivative of x squared, which is 2x. Good. And so what we were able to do again with first order linear differential equations is once we realized that, we basically rewrote this side as d dx x squared y, and we used that. What we saw from there is it basically became a separable equation. We just took the integral from both sides and we worked our solution out. But I want to kind of go back and what do you call it? I want to go back and kind of hover on this idea in this diagram here one way to think about what we have here on the left side of the differential equation is, again, there's almost like a function above it, not just like a function above it, there is a function above it. And when I take the derivative, I get this. All right, so this is where what I was trying to say before is looking at this idea of looking at the left side of this equation and sort of realizing that it's the derivative of some function up here. Wouldn't it be nice if we could use that idea more in general? So like, again, in the last section, we used this as a very specific tool on a very specific type of differential equation that was set up a very specific way. But this thought and this concept should be applicable to a much wider set of differential equations. So not necessarily linear differential equations, but so that's what we're going to look at today is could we find more first order differential equations that are not necessarily linear, but we can basically take advantage of this conceptual idea and procedural idea that the left side of the equation, so basically is there a much larger set of, sorry, I feel like I'm saying the same thing over and over again, but is there a much larger set of differential equations where the left side does happen to be the derivative of some function up here? Because this, again, this was a helpful concept and part of our procedure. So is there a much larger set of differential equations where this same structure, the same concept would play out? And if so, let's see if we can use that structure or concept to actually get our solutions. So that's what we're going to be looking at today. They call these exact equations. And again, unlike the last section, exact equations, the first thing about them is they don't have to be linear. In fact, you'll see with exact equations, we don't even need, so we're going to look at some equations that have a crazy looking, funky left side to them. But the goal is going to be, can we find, one of the first things we got to figure out is there a function we can start with sort of above that when you take the derivative, you get the left side. And often that'll involve a product of two functions, but it doesn't even have to be that. So again, what we're doing today is we're gonna, exact equations are a much basically broader set of differential equations. Broader because the left side is not going to be as specialized. It doesn't have to be linear. Broader because the functions that we're going to see that you take the derivative of to get the left side don't necessarily have to just be products. So we're going to look at a much broader set of differential equations. But they call them exact because the idea is this left side is going to be exactly the derivative of some some phantom starting function that we got to figure out what that is, but that sort of previously existed. So they call them exact equations specifically because of that. So we're gonna the left side of an exact equation has to be the exact derivative of some starting function that we don't know yet, but we have to figure that out. But if it is, so if we can't show that the left side is the exact derivative of some starting function, then we can do some similar work to what we did in the last section, to go solve the differential equation. So I was trying to, like I said, I like to have a narrative. So when I say narrative, you hear the word story, but I like to have like a through line. So something that makes sense on why we're doing what we're doing today. And so this initial part is I'm just trying to give you guys a connection to what we're doing today. Basically, so what I'm saying, what we're doing today basically is what we did on the last video, but a much more generalized version. So we don't need an integrating factor. We don't need it to be linear. We just need the left side to be the exact derivative of some starting function that we got to figure out what that function is. But if that's true, then we're gonna use a very similar playthrough to how we solve the linear first order differential equations to solve these exact equations. So let's look at an example. Let's look at a couple examples. Let me cue up this first one. This is, so in section 2.4, this is number 5 in the exercises. We have 2x squared y minus 3 dx. Actually, let's it's 2x squared. So it's gonna take default times squares. So 2xy squared, sorry, minus 3 dx plus 2x squared. On equals 0, I assume. Yeah, equals 0. And they're gonna ask us to solve this differential equation. So a couple things I want you to notice here. Notice that, so first again, let's compare it to kind of what we did in the last section, or what the equations look like in the last section. So is this a linear first order differential equation? Does this look like a linear first order differential equation? Hopefully you're saying, hello. Like there's a lot of different things going on. First of all, you don't have dx over dy, right? And then these pieces in front, so even if you ignore the dx dy right now, or just treat them in general like they are kind of the derivatives of x, the derivative of y, the pieces that are next to the dx and dy are nowhere near anything like what, what we saw in the last section. In fact, it's really this y squared here that makes this not linear. So overall, this is not linear actually because of this y squared. So what you could do with this equation, by the way, is you could divide by dx, on both sides. Yeah, divide by dx. And the problem you'd run into is this y squared. So this y squared makes this a non-linear first order differential equation. It is first order because you divide by dx and you get dy dx, and that's the highest derivative that you have. But this is not linear. So this to begin with, there's no way to rearrange this to basically solve this like the last section. So you could make an integrating factor, but it would be useless for you. It wouldn't do anything for you. But like I said, what we want to do with the equations today is we want to use, so not the integrating factor, but we want to use the overall the same flow and concept of procedure that we used for first order linear differential equations. We want to look at this left side and figure out, is there a function we could have started with that this left side is actually the derivative of? And so one way to do this is you could actually just look at, so basically what we're going to do here is you could look at each of these coefficients, what's in front of dx and dy, and you could honestly just kind of hack through it and try to figure out, what that original function is. But there's a way to check that there is an original function. So it won't tell us what the original function, but there's a way to check if there is an original function that these are the derivatives of. And so the way we're going to check that is we're going to start with the coefficient we have here. I'll make sure I get this right. Yeah. So the coefficient that you have here, the first thing you want to do is you want to take the derivative of this, but with respect to y. So since this is in front of the dx, so one way to think about it is, again, there is some phantom function up here. That when you take the derivative, just like as it kind of showed you guys in that diagram over there, when you take the derivative, you get these two pieces. Now, because this one has the dx in front of it, it's kind of thinking about taking, again, back to Cal 1 and taking derivatives. It's obvious that whatever this function was, you took the derivative with respect to x to kind of get there, right? And this one, because you have dy, you took the derivative with respect to y. So what we're going to do, the way that you check whether you can find a function up here is I'm going to start with the one that I already took. And if there's a function up here, you took the derivative with respect to x, I'm now going to take the derivative with respect to y. So I'm going to take this function and do basically, I don't want to write dy, but so derivative with respect to y, we'll kind of write it this way. You may have seen this symbol in Cal 3 if you went through that, or even if you didn't go through Cal 3, they might have mentioned it in Cal 1 or Cal 2. This is what we call partial derivative. So we have a function here that you have two different variables in that function, right? It's x and y. So we're gonna take a derivative with respect to y, which means we're gonna in our minds pin the y as the actual variable, which makes x a constant. So the question is, what is the derivative of that with respect to y? And again, what I'm going to do, we won't even pause. I'm just going to pace back and forth for a little bit. See if you can figure out what the derivative of this is with respect to y. So again, what that means is you're treating y as the variable and x is just a constant. So let's see if you can get that. Okay, so let's see where you get. So with respect to y, so I call so basically with respect to y, what I see is I have a y squared function with a coefficient in front of it, and then I also have constant. So with respect to y, that means this constant goes away, that goes to 0. Y squared, when I take the derivative of that, I'm gonna do 2 times whatever I have there, and then y to the first power. So with respect to y, this ends up being 4x, yeah, 4xy. And then what we want to do is we want to go to the other term. So again, with the other term, whatever this function is up here, you basically kind of in pre-production, right? In pre-preparation, you had already taken the derivative with respect to y to get you down to what you see here. So now what I'm going to do is we're going to take the derivative of this with respect to x. Let's see what we get out of that. So take a second. Again, I won't pause, but just work on it for a second. What's the derivative of that with respect to x? What are you thinking? So with respect to x, now when I'm looking at this, so again, this is an x squared function with 2 and y being my constants. This are coefficients. This is a constant. Constant goes to 0. For x squared, I'm going to multiply by 2, bump the power down to 1. So this is going to end up being 4xy. And notice that these match each other. So if these match each other, as long as these match each other, that tells you that there is a function up here that when you take the derivative of it, you get exactly what we see on the left side of that differential equation. So this is our way. So we take the derivative with respect to sort of the other variable on each of these. And as long as they match, that actually guarantees you that there is a function. Like I said, I keep just repeating myself, but there is a function whose derivative is what you see on the left side of the equation. And again, that ends up being the key for the equations we're going to see today. So they call them exact equations because the equations we're going to see today, the idea is this line on the left is the exact derivative. It is exactly the derivative of some pre-function that you started with. But because of that, if I can find what that function is, then I can play a similar game to what we did yesterday or in the last video with first order linear differential equations. So notice that, I mean, we'll see it as we go, but again, notice that, so I'm saying as long as this left side is exactly the derivative of some pre-function, then I can solve it. So what this does, what exact equations do is kind of interesting is that, again, it creates a much larger set of differential equations, especially ones that are not necessarily linear, that you can actually solve. On the other hand, it's still not, notice that they call them exact equations for a reason. So that left side has to be exactly the derivative of some pre-function. And if I'm just writing a bunch of stuff up here, if I'm just writing the left side to this equation, you can imagine it's actually pretty hard to write that left side to be exactly the derivative of some pre-function. So if you just write anything up there, it's probably not going to be an exact equation. But for the ones that it works, the nice thing is it works in general. Anyways, so you still haven't even got through the procedure, but I'm trying to give you some kind of conceptual visualization of kind of why this method is here and what equations it works for, and maybe some of its benefits over the previous methods that we saw in the last two videos, but also the fact that it's still very tailored, right? It's still a very precise method. It only works on some differential equations. But nonetheless, it's going to get you a lot more differential equations than maybe are the methods we saw in the last two videos. Anyways, so Okay, so we now know that this left side is the exact derivative of some pre-function. So now our job is to find this pre-function. Now, kind of like what we did on the last video, so if you want, you essentially can just kind of try to pick parts here that when you take the derivative, with respect to x, you get this, and derivative with respect to y, you get this. But I will say, and you can probably imagine that that'll be decently hard. I'm not saying it's bad, I'm not saying it's impossible, but it'll be decently hard. Especially because now, again, like I said, this works for a much larger general set of equations. So the stuff that we're going to see in front of these dx's and dy's is going to be a lot more varied, kind of crazy than what we were seeing on first order linear differential equations. So again, completely possible for you to just kind of put this together in your head, but not necessarily easy and probably time consuming. So what I want to look at is, let's get a bit more of a procedure, a way to definitely every time kind of take what you have here and go back and find this function without a ton of guesswork, basically. So I'm not saying there isn't any guesswork, but just not a ton of it. All right. So again, what I've done here, notice that this part of the problem, this is not solving anything. This doesn't tell me what, basically what y is. So again, we're solving this differential equation. We're still back to my overall goal is still the same. I need to figure out what y is. This doesn't do that, but what this does is it's a check for me. First, I have to know whether it is an exact equation, whether this left side is exactly the derivative of some pre-function. And this tells me. So this is work that's needed. It just doesn't give you the answer. So, but we need it. So this tells me there is a function. Part of the reason that I'm doing this visually is even if you're not a visual person, I think that the structure here, the picture is going to help you a lot through this procedure. So this is sort of my middle, and I took the derivatives. I went down to check. But again, what this tells me is there's some pre-function that when I take the derivatives, I get these two pieces. So if I want to go back up and find that pre-function, how would I go back up? I know I took a derivative to get down. Good, you would take an integral. So again, that was one of the biggest points that they needed you, conceptual points that they needed you to get out of Cal 1 and Cal 2 is that integrals are the inverse of derivatives. So if you take a derivative and it gets you somewhere, you should be able to take an integral and get you back to where you started, right? And again, that's what we're saying. There's some pre-function that when you take a derivative with respect to x, it gets you here. With respect to y, it gets here. So all we got to do is take an integral to get back up there. So that's what we're going to do. So in a bit of side work, what we're going to do is I'm going to take the integral of this 2x squared y minus 3 dx. So again, I took the derivative with respect to x to get down there, so I want to integrate back up using x. And let's erase this down. That big right now. And then I'm going to take the integral with respect to y, 2x squared y plus 4 dy. And I'm going to use the results of these two to figure out what this original function is. So let's work that. So what I'd like you to do actually is, again, especially so you get the idea of this process. So we need to work these two integrals. And I want you guys to pause on your side. I'll pause on my side, and let's see what we get. Make sure we both get the same thing. Let's do pause that. I again wrote x squared y instead of xy squared. So this should be integral 2xy squared minus. For some reason, I like x squared. I don't know why. The classics, So when you took the integral of this, what did you guys get? So with respect to x, that means, so again, the funky thing about this is that means the y squared is just a constant. If we're talking about x. So, or you can think of it as just a function, but either way, I mean, it's better, not just better, but it's more correct, at least here, to think of it as a constant. So this is like 2x multiplied by some number, which means that number is just going to follow along when I integrate. But the 2x, when I integrate that, I'm going to end up bumping up the power to 2, dividing by 2. So what I'm going to get here, and very intentionally, I'm going to go upward with this. Very intentionally, what I get here is I get x squared times y squared. And then the -3, when I integrate that, that's going to give me minus 3x. Give me a second to, what's the next thing I was going to say? Let me see if I can shortcut. So when I integrate this, I also get a constant, right? So plus c. And so normally we write it that way. Really quick, since I'm integrating with respect to x, and we know kind of from this original function that's there that there's y is present, right? There's a y function there. But again, the y function is just a constant. We're thinking about our function's variable being x. Then instead of just c, or instead of just thinking of this as like, oh, there's a constant there, the way you want to think about this is actually that there's some possible function of y. So I'm going to write g of y here. So there's some possible function of y there. Now, maybe there's nothing there, but the idea is basically if there was a function of y and you took the derivative with respect to x, that's just a constant. So it would have gone away when you did this work to get down to dx. So there's possibly a function of y up here. And we'll use that as a replacement for the overall constant. Now that function of y could have an actual just straight number there. It could be a constant or it could have a constant in it. So we'll just sort of roll that into this piece here. So when you integrate, there's some random constant could have been there. But in this case, since we're integrating just with respect to x, that constant could be a function of y. So there could be a y there, basically. All right. Now on this side, when we integrate, so we're integrating with respects to y. So again, notice that this x squared, and really the 2, but this x squared is just a constant. So you have a 2x squared, you have just a nice little coefficient in front of y. And when you integrate that, you're going to bump the power up to 2 and divide by 2. So you're going to end up with x squared, y squared. The 4, when you integrate that with respect to y, you end up with 4y. And now, since you're integrating with respect to y, again, there's going to be plus c, some constant, but that constant could be a function of x. It could involve x because with respect to y, x is just a constant. It's not even really a function. It's a number. So there could possibly be a function of x here. I'm using g and h here. It doesn't really matter what you say there. Like what letters you're using there. They're just functions. But what I'm saying is the constant here could be something with an x in it. So if I integrate, so going back to kind of what we're really doing here, if I integrate both of these coefficients, so if I integrate both these functions backwards, what I'm saying is, again, I know to begin with, because of this work, I know that there's a function that when I integrate it with respect to x, I get this. With respect to y, I get this. So what we did is we just said, well, let me go in reverse. Let me take a integral, you go back and try to find that function. And notice that when you look at these two answers, they're really, really similar, right? So they both have x squared, y squared. So in some sense, that's the first thing, is you gotta be like, bingo, I got it. So x squared, y squared. Now this one has a minus 3x and this one doesn't, but remember that the one on the right side, you could have had a function of x. That it's just a constant when you take a derivative with respect to y. So there could have been a function of x here, and we're not going to see it when we integrate, right? And then notice that there's a 4y on the right, and there isn't a 4y on the left, but there could have been a 4y. So what I'm basically saying is there's a minus 3x on the left and not on the right, but the minus 3x could have been there. We already told ourselves there could have been a function of x. We wouldn't have seen it when we take the derivative because it would have went to 0. And vice versa, there's a 4y on the right, and it could have easily been there. So basically the 4y takes the place of this, the 3x takes the place of that. So overall, I've found the function. So I've got it. It's going to be x squared, y squared. It's going to have the minus 3x, because again, that would have been here, and it's going to have the 4y, because that would have been that would have been here. It's going to have the 4y because that would have been there. So overall, I've got my function. X squared, y squared, minus 3x, plus 4y. When you take the derivative of that, so when you do the, well, yeah, we'll just say when you take the derivative of this with respect to x, you get 2x squared y minus 3, and when you take the derivative of this with respect to y, you get 2x squared y plus 4. All right. Now, so the next thing to note is we took the integral, we kind of took the integral both ways, but we took the integral to get us back to this function. So we also want to mark what happens on the right side of the equation. So we will be taking the integral of 0. And whether we're doing that with respect to x or y, if I take the integral of 0, what does that give me? That gives me a constant. And notice that this equation that we've come up with doesn't have any derivatives of it in it, and it has y in it. So this is actually our answer. So they asked us to solve this thing. And give me a second, let me just figure out how I want to explain the next one. Okay. So I think the thing that I want to explain here is, so again, so like we did in the previous video with linear first order equation. So we would find, we find whatever this original function was. But what we did with those, I would write d dx of that function equals, and then whatever's on the right side, and then we integrate both sides up. So I guess one thing I want to emphasize about what we just did here is we kind of did that same thing, but we didn't have to write integral of this and da da da, because in finding the integral of both these parts here, kind of backwards integrating, we kind of did that here. So we don't need now this extra step of kind of taking this and writing d dx and integrating it, because we know we're just going to get back to this function anyways. So what I'm saying is, once you've got this, there's your answer. Because we integrated the left side, we integrated the right side. The difference that you're going to see here, I would say one of the big differences you'll see with a lot of the equations, these exact equations in this section of it that we're solving, compared to what you saw at the end of those, what do you call it, the first first order linear differential equations is that not just with the first order linear differential equations, but you think about those first two sections that we did, 2, 2, and 2, 3, when you solved it, you got what you were, we talked about your goal is to figure out a solution for y, right? So you got a nice function of y that was in terms of x. One of the big differences you're seeing here is, so I'm saying this is the answer. The problem is, does this look like the way we normally write a function? But that's not the way we normally write a function. We would normally have y equals and then that. And the thing is, so you can go ahead and try to solve this for y. Let's shortcut it for you, again, especially because this is a 5 weeks class to get through this lecture. If you try to solve this for y, you're not going to be able to get y by itself. Especially because we have these y and y squared, kind of these unlike terms. So you have not only the function y that you're looking for, but you have the function y squared. And they're all mixed in with these x terms, some with the x and some with an x squared. And so basically what happens here is this, just from an algebra standpoint, you try to solve for y, you're not going to be able to. Now, back in Cal 1 and Cal 2, especially in Cal 1 is when they introduced it, that doesn't mean this is not a function. It just means that one, so there's two ways you can think about it. This is a function defined both in terms of x and y. So you can think about it maybe in a Cal 3 perspective. It's a it's a function defined on two variables. But even minus that, you can just think of this is an implicitly defined function. So back in Cal 1, we talked about implicitly defined functions and doing implicit differentiation, which is actually a little bit of what we're doing with these partial derivatives. So this is just an implicitly defined function. There are some functions that we can't define cleanly as y equals and then a bunch of x's on the right side, right? There are some functions that it's a function, or at least maybe it's a relation, but it's a function that you can go ahead and graph this thing. Throw this in a calculator, you can get a graph going. But I can't isolate it to y equals blah, 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 x, or x equals blah, 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 y. And that's fine. The thing exists. You can graph it. The thing exists. It just doesn't, we don't get this nice clean way of writing it, essentially. So that's what you're going to find often with the solutions. And I won't say every time. Sometimes you're going to get a solution here where you can get y by itself. And basically, if you can get y by itself, then as usual in mathematics, we'd like you to do that. We want you to define it that way. But if you can't get y by itself, it's completely fine to leave it as an implicitly defined function. And that's what we have. So my answer then, so they ask you to solve this thing. My answer is x squared y squared minus 3x plus 4y equals c. Or else, I was looking in the book in y'all's homework. Often what they do is they'll basically subtract the c and move it to this side. Now, if you subtract a constant, you just get another constant. So when they move it to the other side, they'll write it as plus c. It's just a negative of whatever it would have been otherwise. But this is another way to write it so that you have a 0 on the right side. And sometimes they like to write it that way. There's a lot of different purposes, a lot of different reasons why this is kind of a convenient way to write it. But either way, this says the same thing. Either way, this is our solution. So I think that's, like I said, I just put pause because I want to make sure the big connection I want you to make out of this, kind of the end of this process. So again, the overall process for solving an exact equation. You first take partial derivatives of each side to make sure that they match. And if they match, that tells you there is an answer. There is a function. Then what we did is we took the integrals of each of these parts to work our way back up to what that function is. And then we also just took the integral to 0 on the right side here to just get us to do the integral on the right side. But once you've done that, again, kind of unlike what we did for linear first order differential equations, you got your answer. Because the integral undoes the derivative. So by doing this little integral work here, you're actually finding the answer. So hopefully that connects for you. I feel like this is one of those that probably really easily connects for you. And in my mind, I'm just thinking that I'm missing some sort of connection, which is why I keep trying to explain this. But good. So if it is an exact equation, this is how we're going to check for it. If it's an exact equation, then we can solve this. And like I said, so notice that now we can solve a much broader set of differential equations, including ones where the function is not defined, as a nice classic function. They're implicit functions, so they're functions of two different variables. So let's practice with a couple of these. That's all we really need. I really wanted to spend some time on this first one to make sure you kind of get a picture and an idea of that process down, because then, like the last section, so once you have a picture of the process down, it's going to work the same every time. All right, so that was 5. I think the next one I wanted to do, the next exercise, that's a good example is, let's see, let's do one with some different parts to it. Let's do number 9. X minus 1. X, y cubed plus y squared sine x. This I assume is, what is it? Also, give me, is there something else you'll need to see with this? Or is it fine that way? Hmm. Sure, dx. That's a dx. That's y squared. Make sure I wrote that right. Okay. So they're gonna ask you to solve something in this. Notice really quick, what's maybe one small difference between how this equation is written and how the last differential equation is written? Good, so instead of having everything on one side equals 0, we have one side equals another, but that's an easy thing to remedy. So we do want it to look like the last one, just so we can check the derivatives and then do the integrals. So we can just move this onto the other side. So what I'm going to do is I would essentially be subtracting the right side to move it onto the left side. So what I'm going to do is I'm just going to rewrite this with what you end up with there. So we subtract, we have equals 0. All right, so the first thing is, again, we need to take the derivative of each of these to check if this is even an exact equation. So this one on the left, because it's in front of dx, you're going to do the partial derivative with respect to y, and the one on the right, because it's in front of dy, you're going to do the partial derivative with respect to x. Second two. Try to make that look a little better. X. So that's the first thing I want you guys to do. Go ahead and pause on your side, I'll pause on my side. Do your partial derivatives here, and let's check that we get the same thing. And let's see what you guys got. So on the left, so with respect to y, that means x is a constant. So that means that x goes away, goes to 0. Should have ended up with negative 3y squared, so we're doing a derivative there. Also, notice that means sine of x is also a constant. But it's basically in front of y squared, so it's a coefficient. So that's gonna stay. That's just gonna drag along. So you should have got negative 3y squared, or negative 3y squared, plus it'll be 2 sine of xy, or 2y sine of x. And then on the right side, we're taking the derivative with respect to x. So with respect to x here, notice that oh yeah. As you're starting to do this derivative, I think the one thing you got to note is you do have this minus in front. And that minus does factor into our derivatives basically. Because on the previous one that I showed you to begin with, we kind of had a plus between, not kind of, we did have a plus between the two. So by having the minus here, what I'm really looking at is this is a plus, and then basically you want to distribute the minus. So it's going to be negative 3xy squared, and it's going to be negative 2y cosine x. Another way to think about it is you could have taken the derivative with respect to x as it was written, but you still would have had to multiply through by a negative. So essentially what I'm doing here, and you can do it either way, you can multiply through by the negative at the end, but essentially what I'm doing here is I'm distributing the negative to begin with, so that for me personally, I just like the thing to match. I don't want to have to do extra work at the end, basically. So I'm going to distribute the negative to begin with, but then when I take the derivative with respect to x, so again, now y squared is just a constant, it's really coefficient. The derivative of negative 3x is negative 3. But also then with the y squared. So we get the negative 3y squared. And then with respect to x, this negative 2y again is actually just a coefficient. The derivative of cosine x is negative sine x. So that's going to give me positive 2y sine x, which is exactly what we see. So again, we just had to check. We have to check that we get the same thing both ways. And you do. Make sure you guys can see all the way over there. Yeah. And if you can, then that means what I'm going to do is I'm going to take each of these and integrate back up, sort of the opposite way or the opposite variable, but I'm going to integrate back up. Or sorry, not the opposite variable, the variable you see here. I'm going to integrate back up and kind of not only just comparing, sort of, rectifying those two solutions with each other, we get the overall solution. So I'm going to integrate back up on the left side. I'm going to integrate back up on the right side, but the integral of 0 is just a constant. So that's what we need to do next. I'm going to integrate. Yeah, I guess I'm going to integrate. And I'm going to integrate this. And I'm going to integrate this. And then I should end up with a nice solution. So that's the next thing I'll have you guys do. So pause on your side. I'll pause on my side. Integrate these two. And then again, kind of figure out what's common between them and what pieces you need to make both of them match. And you'll have your solution. So go ahead and do that. Check on it. All right, so let's see what you have. So we are going to integrate this one with respect to x since it has the dx. So what you should have got there was x squared over 2. The y cubed is just so here's kind of the fun part here. The y cubed is just a constant. So you actually get y minus y cubed x. And then the y squared is also just a constant. So you're really just integrating sine x here. So you get minus y squared cosine x. And then possibly some function of x there. That would have been a constant anyways, because it only had an x in it. So when you took the derivative, it went away to get to this form. All right, and then on the right, we're integrating that one with respect to y. Looks like, so again, the -3, the x are just constants, the y squared goes up to y cubed, and you divide by 3. So again, what I see, second. Oh, yeah, minus, isn't it? Is negative y cubed with an x there. This is another reason, by the way, that it's good to distribute that negative. Again, when you're doing this integral, you could do the integral. So going back to having the minus in the middle here, you could have done the integral, but you'd still have that minus, so it ended up distributing through at the end. So I guess really either way that you like to do it, but I kind of prefer to distribute it first so that when I do the integral, I'm done. And then this part here, so again, the cosine x now is just a constant, so it's the 2, their coefficients. You're integrating, oh, I'm sorry. This should have been g of y, g of x. So some function that just has a y in it. But you have the 2, you have the cosine x, so nothing happens to those, but the y, when you integrate that, you'll get y squared over 2. So you end up with minus y squared cosine x. And then with this, there could have possibly been some function that had an x in it that when you took the derivative with respect to y, it just went away. Now on the right side, and again, integrating a 0 just gives you c. Now comparing these, notice that again, voila. Yeah, that's why they call this an exact equation. So it just happens to work out kind of perfectly, right? So negative y cubed x matches, your y squared cosine x matches. Notice on this one, so we do have an x squared over 2 here, which is basically our missing piece here. But there isn't an extra piece over here with a y that we, that's our missing piece here, and that's okay. So again, when this g of y is really just when we integrate, we have a constant, and it could have been there, but the constant could have also been 0. There could have been nothing there. When you integrate nothing, you still get a 0. So you just don't know if there was something with a y there that when you integrate goes to 0, or if there was nothing that also goes to 0. So basically, again, just looking at these two, it looks like here I was missing this piece, so that's part of my answer. I wasn't missing anything here. So overall, and this is where I need to move this. A little too far. That'll be good enough. So overall then, my answer is, doesn't matter the order here. So x squared over 2 minus y cubed x minus y squared cosine x all equals c, and that is my answer. All right. And then we can do this again. This time we'll do a initial value problem. So again, what you're seeing both times with solving these exact equations is you, just like all of our other differential equations, you get the c at the end. But realistically, if you're working on some actual problem, some actual system, some engineering, physics, chemistry, etc., you'll likely have some initial condition that allows you to get not this general solution, but actually figure out what C is and get an exact solution. So let's do that. Let's kind of do one like that. Yeah. Let me just pick one like this. there anything special? Is there anything special y'all need to see with this problem other than initial conditions? Do you want what to do that? All right, so let's do, I wanted to do one with a little more complexity, but I just need the right combination here and I'm sort of make it my own. So anyways, let's do, um, one says we have x plus y squared, dx, yeah, and two x y. Where are we going? 2xy plus x squared minus 1. That's going to be dy, and all of this equals 0. And then I'll move the camera because you're not going to be able to see all this. Or at least all of it towards to the end. There we go. And then the initial condition here is that y of 1 equals 1. So when x is 1, y is 1. So this is our differential equation. We want to solve this with this initial condition so we can get the exact solution, particular solution. But the play is exactly the same. So you know kind of the routine now. You need to take your correct partial derivatives here to see if it matches. And if it does, then you need to take your integral back up. Get your missing parts to jive. And that'll be your general solution, and then we just need to add on this part at the end. So I want you guys to pause. I'll pause on my side. See if you can go all the way through it. And we'll come back, I'll go all the way through it and just make sure we haven't hit all the marks. All right, let's rock and roll our way through this. So the first thing is I'm going to take partial derivative with respect to y here, partial derivative with respect to x here, see if I get the same thing. So taking the derivative with respect to y here, you got a little bit of chain rule, sort of barely, because this is, again, this is not y squared, this is x plus y squared, so think of this as like y plus a number squared. So really you have an overall a squared function, power function. So the derivative is going to be 2 times this, but then times the derivative of x plus y. But the derivative of x plus y with respect to y is just 1. It's whatever the coefficient is in front of y. So this is going to end up being 2 times x plus y. Or 2x plus 2y. Now on the right side, you're taking the derivative with respect to x, so you get, what do you call it? So here, you're going to go down in power, so you're just going to get your coefficient left. So here, you're going to get 2y. Derivative of x squared is 2 times x. Derivative of -1 is 0, and notice you got it. 2x plus 2y. So this does check out. Since that does check out, I will do integrals back up. So the integral of this, so now you're doing the reverse process for chain rule, which was substitution in general. Not every integral that came from, or derivative that came from chain rule you can work using substitution, but most of them. So, but basically, so we're going to do substitution here. We're sort of our function. And now, first of all, we're integrating with respect to x, and our function inside of the squared function is x plus y. So the derivative of x plus y is 1 dx. So the key thing is that means the dx is enough to be able to, as the derivative of x plus y, so we can work our way back up. So the integral of this is going to be, you raise the power, divide by the power, so this is going to be x plus y cubed. Sorry, give enough room for this. Yeah, it's going to be x plus y cubed all over 3. Plus possibly some function of y. And then when I integrate this with respect to y, so I'm going to end up getting what, a y squared. So I'm going to end up getting x y squared over, I'm sorry guys, I'm hungry right now. My mind is kind of starting to vaporize. So this goes up, you divide by 2, so it's just going to be xy squared. Give me a second, I'm missing something with that first integral, or I'm not seeing something. You know, so we get x y squared, and then x squared y, then minus y, and then plus possibly some function of x. This side just ends up being c. So we've got to make these sort of jive with each other. Seems like there's still a problem just divided by 3. What's the problem here? Oh, did I not write something down? That's possible. No. All right, so on first look, so you've done your integral. On first look, these don't look very much like each other. So honestly, it's tempting to kind of be like, well, not just tempting, I mean, it's a good thought to be like, okay, what's going on here? These, every time up until now, these have kind of matched well, and these definitely don't look like each other. The one thing we want to check then is, so right now I have this written out in basically factored form, and I have this written out sort of what they call standard form with everything distributed and multiplied through. So the kicker is I'm going to have to go through and actually do this, do x plus y cubed. I need to actually distribute this out. And we're hoping then that when I do that, I end up with similar pieces that I see over here. So, to shortcut this for you guys, so when you multiply this out, when you do x plus y cubed, and make sure I get this right, you end up getting n by the way, every piece that I'm gonna put there then is divided by 3. So let me kind of factor that in. So what you'd end up with is x cubed divided by 3. And then when you do all the work out, you'd end up with plus 3x squared y divided by 3. Then plus 3xy squared divided by 3. And then plus y cubed divided by 3. And notice, so the reason I'm writing out the divide 3 is just so you kind of see not only the action, but kind of catch the pattern here. That those 3's cancel, and notice that now this x squared y does match this, and the xy squared does match this. I want to make sure minus y. Sure. Minus y. Second, what is going on with this 1 cubed over 3? That's fine. That's part of it. Let me see if this card works out. Works out. Multiple like you over 3. So we figured out, said what was wrong. There's this one piece here that basically wasn't showing up, and what I kind of knew kind of had to be not just, but like what I knew had to be the answer. So this y cubed plus 3. So really quick, I want to talk about how I realized this, and then sort of the way I'm going to work at solving the issue. Oh man, hold on, I'm really hungry. Give me a second. All right. So what I noticed is that, so again, if these are my 2 parts, so we have, notice over here, we have the x squared plus y, we have, or xy squared and x squared and y. We're missing an h of x, which is the x cubed plus 3. And we have this minus y, which is, would seem to be this piece over here, the g of y that we're missing. But notice that y cubed plus 3 also only has a y in it. So if y cubed plus 3 was part of the end answer, it would show up here as well. And it doesn't. Or it would somehow, Yeah, I mean, basically it would show up here as well and it doesn't. So that's kind of what struck me as I was looking at this is when I was trying to match the pieces to each other, again, because these derivatives match, we actually know that there is an exact solution. So it also can't be that because of the y cubed plus over 3 that there isn't a solution. There is a solution. And everything seems to match. So like I said, xy squared, x squared y, xy squared, x squared y, x cubed over 3 minus y. Just write this up here. But this y cubed over 3 is kind of our outlier here. So what that tells me is, again, this can't be part of the solution because you would have ended up seeing it here. But I think then there's a legitimate question of how the hell is that not part of the solution though, if when I expand x plus y cubed over 3, I do get it, right? That's part of the expansion. So I want to talk about when you expand x plus y cubed over 3, a second. Let me just figure out. This is where it's why I had to pause the for a second, just figure out how to explain this to you guys, because there's some decent mathematical conceptual fun to this. So give me a second. Hmm. No, I mean this still gives us a y squared, which is what you would get out of that. Like you, the problem is you're not integrating, you're not taking the derivatives with respect to y, so it still should go to 0. Honestly, I just really think honestly that they wrote this wrong. I mean, it works out. The integrating the derivative works out, but I think they honestly wrote this wrong. Oh. Oh no, if you do end up with the y squared. Never mind. Sorry. Yeah. Sorry. I just worked some of that out in my head. All right, so basically, I think I'll sort of have to leave the explanation at essentially, you can kind of confirm that if the y cubed plus over 3 was part of our overall solution, then when you take the derivative with respect to y to get this piece here, you would end up with a 3y squared over 3, which is y squared. You basically end up with a y squared, and you don't. Now, without this piece, then the rest of this checks out. So if you have x cubed over 3, so again, like I said, x cubed over 3 is filling in the role of this h of x, minus y is filling in the role of g of y. You have xy squared and x squared y in common. So you can maybe think of this like an extraneous solution when we're solving some stuff in algebra. But basically, the ones that overlap are definitely there, and the two functions from each side, one just of x and one just of y are there. But we can confirm that the y cubed minus over 3 isn't part of my overall solution because it would have came down on this side. We would see it here. See the derivative of it. Anyways, so what this all tells me, looking at these two, that my overall solution is x cubed over 3 plus xy squared plus x squared y. What was the other one? Minus y, and all of that equals c. So this is my general solution. And again, so I just part of this is I'm sure you guys got it, but in my head I keep thinking that I didn't explain it well enough, or that I made some jump mess out of it. But again, one thing you're seeing here that we didn't see on previous problems is sometimes you do end up with sort of basically an extra piece here. So we had to distribute out the x plus y cubed over 3 to make sure it matched some of these other pieces here. And you did get x squared y, and you did get xy squared. You got x cubed over 3, which is fine because that's your h of x. And this minus y is fine because that's your g of y. But we ended up getting this extra piece, y cubed over 3, that so again, that should surprise you for a second. So we get this extra piece that if it was really there, then when you take the derivative according to y, you would have seen it in this right here, this part of your differential equation. And you don't. But we know there is a solution. So basically, that's just not part of our solution because it doesn't match up. So our solution is x cubed over 3 plus xy squared plus x squared y minus y equals c. And now I can take all that. So what I'm going to do here is I'm going to take all that, and this is my general solution. I'm going to plug in my information to get my specific or my exact solution. So plugging this in, we have what, 1 for x and 1 for y. So we have 1 cubed over 3 plus 1 times 1 squared plus 1 times 1 squared minus 1 equals c. And actually, we just got to kind of work that all the way through. So what you end up getting here is 4/3 equals c. So then my overall solution, my final exact solution here is x cubed over 3 plus xy squared plus x squared y minus y equals 4/3. And this is indeed your exact solution to that differential equation. All right, good stuff. So you guys kind of get the idea. That's how we solve the exact equations. As long as, again, doing that first check, in each of these, you had to take the partial derivatives at first so you can check if it's an exact equation. But once you know that, then that's how you solve it. So we will come back for one more video for this week on equations that require substitution, which will mirror one of the ways of solving differential equations that we've already. So I'll see you guys for that one.